Hello there. In this very short video, I want to go back and have a quick look again on the system type of a unity feedback system that we have already discussed in the previous few videos. So please, I recommend you to refer again to the topic on unity feedback systems and system types if you need to refresh your memory. So please feel free to stop, to pause this video and go back to that video first before we could continue the discussion. Okay. Apparently, you still remember. I think you still remember from the discussion in that previous video. A system type in a unity feedback system and its associated static error constant will give us an idea on how the steady state response of that corresponding system will behave with respect to a certain input signal. I think I will pop up again the slide, one of the slides in the previous video on when we were discussing system type. You still remember this table? If, let's say, we have a unity feedback system, where the open loop transfer function shows us that the unity feedback system is a type 0 system. Okay. If a step input is given to the system, to type 0 system, we will have a constant static position error constant, right? The static position error constant Kp will be a constant value, and this will bring a consequence that the steady state error of a type 0 system when a step input is given will be constant, will be a finite value. The steady state error will be finite. That means if to this type 0 system a step input is given, there will be a finite, a constant steady state error in the step response. Which means again, this type 0 system can follow the response can follow the step input, but with a certain constant finite difference between the response and the input. If a step input is given, it can follow the input, but with a certain difference. Okay. But if to the same system, type 0 system, RAM input is given, apparently for type 0 system, the static velocity error constant, the Kv, will be equal to 0. This brings a consequence that the steady state error will be equal to infinite, which means if to this type 0 system RAM input is given, the steady state error will be infinite. Or in other words, if RAM input is given to this type 0 system, the steady state response definitely cannot follow the input, the RAM input. Okay, so type 0 system definitely cannot follow RAM input. Same thing if a parabolic input is given to the system, to the type 0 system, we will also have a 0 static acceleration error constant, and this will bring a consequence again that the steady state error will also be equal to infinite value. Same conclusion like before. If to a type 0 system a parabolic input is given, the response definitely cannot follow the input at all. On the other hand, if we have type 1 system, if we have a unity feedback system where the open loop transfer function tells us that the unity feedback system is a type 1 system, if a step input is given to a type 1 system, the static position error constant Kp will be equal to infinite, which means that the steady state error will be equal to 0. The steady state error of the step response in our type 1 system will be equal to 0. What does it mean? The error is 0. There is no difference between output and input, between the response and the input in steady state condition. That means, again, because the steady state error is 0, for this type 1 system, if a step input is given in a steady state condition, the response can follow the input, the step input, very well in steady state condition. For the same system, type 1 system, if for now RAM input is given, we will have a constant value for the static velocity error constant Kv. This will bring a consequence that the steady state error of the response will be equal to a finite value, 1 over Kv. What does it mean? This means for this type 1 system, if RAM input is given, the response still can follow the input, but with a constant error, with a certain constant difference between the response and the input in steady state condition. On the other hand, if a parabolic input is given to a type 1 system, okay, the static acceleration error constant Ka will be 0, and steady state error due to this parabolic input will be equal to infinite. What does it mean? This means the steady state error will be infinite. This means, again, in the steady state condition, the response definitely cannot follow the parabolic input at all. Okay. Now, if we have a type 2 system, if a step input is given to this type 2 system, the static position error constant Kp will be equal to infinite value. This means the steady state error will be 0. Again, what does it mean? It means for this type 2 system, if a step input is given, there will be no steady state error, because the steady state error will be 0, which means, again, the response can follow the step input perfectly without any difference. Same thing will happen if to this type 2 system a RAM input is given. The static velocity error constant will be infinite. The steady state error will be 0, which means, again, to this type 2 system, if a RAM input is given, at the steady state condition, the response can follow the RAM input very well without any difference between the response and the input and the RAM input. However, when a parabolic input is given to this type 2 system, we will have a constant static acceleration error constant Ka, which brings a consequence that we will have a finite steady state error, which is equal to 1 over Ka. This means, again, if to this type 2 system a parabolic input is given, the response at the steady state condition still can follow the parabolic input, but with a certain finite difference between the response and the input. Okay, so this is the a table that we need to go through again to refresh our memory. Now let's go back to the original slide in this topic. But now, how can we estimate that system type properties in terms of static position error constant, static velocity error constant, and static acceleration error constant of a system or of a unity feedback system that is stable? What does it mean when I say stable? Based on the frequency response function, if we have a stable unity feedback system, that means the gain margin as well as the phase margin, both of them have to be positive, right? Okay, we have a positive gain margin and phase margin, which means we have a stable unity feedback system. The question now, can we estimate, can we predict the static error constant in terms of static position or static velocity or static acceleration error constants? Can we estimate those based on the Bode plot of the open loop transfer function in our unity feedback system? That is something that we are going to answer in this video. The answer is yes, we can estimate based on the low frequency region of the magnitude plot of the open loop transfer function in our unity feedback system. This plot, this magnitude plot, eventually can be used to estimate the associated static error constants, and eventually, of course, we can correlate it with the steady state error. So how to do that? Let's take a look in the next few slides. Let's start with a type 0 system, and then we are going to estimate the static position error constant Kp from this type 0 system. So now we have a type 0 system, a unity feedback system where the system type is equal to 0. A typical magnitude plot of the Bode diagram in a type 0 system will be something like this. What we normally see if we have a type 0 system at low frequency region, the magnitude plot will have a zero slope magnitude plot like this, only at low frequency region. So for sure, if you have a type 0 system at low frequency region, the magnitude plot will have a zero slope like this. Okay, for type 0 system. Now, how do we estimate the static position error constant? It's very simple. The static position error constant apparently can be estimated roughly based on the asymptotic value of the magnitude at low frequency region. So you just simply have to extend this line until it crosses the vertical axis, and then this value where it crosses the vertical axis will tell us the static position error constant. The value that will be indicated in here is the static position error constant in dB scale. Of course, it will be in dB scale because magnitude plot is always presented in dB scale, right? So what we have to do, if you want to identify or if you want to estimate the static position error constant from type 0 system, you just have to find where the extension of the magnitude plot at low frequency will cross the vertical axis. This value will tell us the dB of the static position error constant. Right? It's just as simply as that. What about type 1 system? For type 1 system, we can also estimate the static velocity error constant. Same like type 0 system, type 1 system has a unique characteristic. Typically, the magnitude plot of the Bode diagram in a type 1 system will have negative 20 dB per decade slope at low frequency region. At low frequency region, your magnitude plot should start with a line with a slope of negative 20 dB per decade. And how do we estimate the static velocity error constant, the KV? Again, it's pretty simple as the previous case. What we have to do, you just simply have to extend this line, the magnitude at low frequency region, extend it until it crosses the horizontal axis, until it crosses the frequency axis. Let's say this extension will cross the frequency axis at omega v. How do we estimate the static velocity error constant? Very simple. The static velocity error constant is equal to the omega v there. Okay, so you just simply have to extend this magnitude plot until it crosses the horizontal axis, and you just simply have to read where it crosses the horizontal axis. The point where it crosses the horizontal axis will tell us the static velocity error constant. What about for type 2 system? How can we estimate the static acceleration error constant from the magnitude plot of a type 2 system? It's pretty similar to the previous two. For a type 2 system, we have also a unique characteristic in its magnitude plot. Typically, for type 2 system, at low frequency region, we have a magnitude plot with a slope of negative 40 dB per decade. So slightly different than compared to type 1 system, where at low frequency region, type 1 system will have a slope of the magnitude plot equal to negative 20 dB per decade. For type 2 system, the slope of the magnitude plot at low frequency region will be equal to negative 40 dB per decade. And how to estimate the static acceleration error constant? Pretty similar to the previous case when we estimated static velocity error constant from type 1 system. What we have to do, we just simply have to extend this line again until it crosses the frequency axis. Read the frequency where this extension crosses the frequency axis, and the static acceleration error constant just simply equal to this frequency squared, omega a squared. Okay, so that's how we estimate static error constants based on the Bode plot of the open loop transfer function in our unity feedback system. Just to conclude here, I would like also to conclude a few points from our previous short videos. In most cases, analysis with a Bode plot of an open loop transfer function in our unity feedback system will give us pretty good idea on a response of closed loop system, of the closed loop system, right? The Bode plot of our open loop transfer function, on the one hand, can tell us the property of the transient response in terms of zeta and omega n. These are discussed in our previous video, because zeta and omega n can be calculated from phase margin and phase margin and phase margin frequency. Phase margin and phase margin frequency can be inferred from the Bode diagrams of the open loop transfer function in our closed loop system. Once we have already identified the phase margin and the phase margin frequency, based on a few equations that we have already discussed in the previous video, you can associate it with the damping factor, damping ratio, and the undamped natural frequency of our closed loop system. So by observing the Bode plot of the open loop transfer function in our unity feedback system, in the one hand, we can have a good idea on how the response will look like in transient stage, because transient stage is characterized by zeta and omega n. On the other hand, this Bode plot can also tell us a very rough idea on how the behavior of the closed loop system in steady state condition in terms of static error constants. Okay. At low frequency asymptotes, the low frequency asymptotes of the magnitude plot in our Bode diagrams will tell us the idea of the steady state error. This is something that we just discussed, because steady state error can be inferred from the associated static error constants. So once we know the static error constant, we should be able to estimate the steady state error, right? To conclude our last few videos, gain margin and phase margin will tell us the stability of the closed loop system. So if our closed loop system is stable, the gain margin and phase margin that can be observed from the Bode diagrams of the open loop transfer function in our closed loop system, both of them have to be positive. Open loop frequency response, from our open loop frequency response, phase margin and phase margin frequency, just like what I have already discussed before, will give us an idea on the two most critical parameters in our system: the undamped natural frequency omega n and the damping ratio of zeta. This part were discussed in the previous video. Okay, so this concludes this short video, and then in our next videos we will discuss on how to design controllers for any systems.